Price, who's going to be giving the first lecture of a lecture series, which will be ongoing, hopefully, in perpetuity. And this is lecture series as part of the Fire Centre that we're developing at the University of Tasmania, which is a large sort of cross-institutional centre which is going to have a lot of linkages with different stakeholders in government, NGOs, practitioners. It's, I think, very timely that we're beginning to think about the fire issues which are confronting not just Tasmania but Australia. And one of the catalysts, I suppose, for developing the Fire Centre is the fact that the University of Tasmania is a partner in a New South Wales government-funded fire hub, which is directed by Ross Bradstock, who's here with Owen, and we're talking about some of the work we're doing in New South Wales today. So, and Owen will be talking about his research primarily, I imagine, in the Sydney Basin, which is very transferable fire risk issues, which are certainly confronting the capital of Tasmania, Hobart, and probably Launceston is equally at threat to catastrophic fire damage. So yeah, it's a very short notice. What we're hoping to do is, as we get visitors coming, get a lot of people coming involved in our research at global and national level, to get them to give a seminar and just start initiating more networking. We're wanting to have some social activities. Jen Steiger has been a prime mover. I don't think she's here today. She's started a new job, which is actually rather convenient because it means she's in government and left the university, but will be still connected with the Fire Centre. So that's the background. Owen and I, we were just reminiscing. We've known each other for over 25 years. We worked together in Parks and Wildlife in the Northern Territory Government. We've written papers together. We've collaborated on, I think, at least 3 ARC linkage grants. And it's really exciting to have another 5 years of being able to work with Owen. He's a highly accomplished statistical analyst who brings sort of statistical rigour to very complicated ecological problems, biodiversity problems, landscape scale problems, and basically carbon problems. So fire is a perfect sort of subject for somebody like Owen, and we're very lucky to have, we need lots more Owens, and we're very lucky to have him give a talk. So thank you.
Thank you, Dave. That was a lovely introduction. So I'm going to talk to you, give you an overview of bushfire risk, the science of bushfire risk, where we're up to at the moment. And it will be some of my own research and from the team at the Centre for Environmental Risk Management and Bushfire at Wollongong, but there's some other things as well. So as an overview, I do apologise if it's not in a great deal of depth, but certainly feel free to ask any questions afterwards. So what do I mean by bushfire risk? Well, risk is officially classified as the combination of likelihood and consequence, or probability and impact, as you can see in this sort of diagram, where you get the red areas where you've got very high likelihood, so almost certainty, and catastrophic impacts, that's very high risk. In terms of what I'm actually going to talk about today, I'm really going to be talking about the direct fire impacts on people and properties, and some stuff on smoke, because smoke is an area that I've been working in recently and will be in the next few years as part of this hub that Dave mentioned. But there, of course, there are other impacts from bushfire, including economic impacts, social impacts, so people's well-being. People are studying all these aspects, and of course biodiversity, which is one of the big ones that I won't really be going into any detail. So as I see it, the big challenges are, if you want to understand bushfire risk and how we can mitigate, you need to focus on 3 big areas. The first is risk planning, so that's understanding where is at most risk. And as you can imagine, that's not a trivial task in itself. The next thing is you have to know when fires are likely to occur, so you can be ready for them, so that's forecasting. And then the third thing is you have to know what is going to happen. So what the actual impact of the bushfire is. And once you've got all of those things in place, you can start to talk about mitigation, what you can do to reduce that risk. I have stuck in that extra one there because once you've got all that sorted out, you can get into this field of balancing competing objectives, because although I'm not really going to talk about it today, some of these values, like biodiversity values, for example, could be require different types of fire management than, say, people and property. So there is a whole field of research and management that's about balancing those objectives, but I'm not going to talk about that today. So this is some examples of forecasting and planning and what you do about it, so mitigation. Now, the first thing I say before I go into any of this is that fire is extraordinarily complicated, and that's the challenge we're dealing with. So just as an example, this is a bushfire. This is the sort of thing we're trying to mitigate against, I guess. This is a bushfire, and these could occur in the same place, but on different days, obviously. So some of our information about where fires occur, they could be treating these two things as exactly the same sort of thing. Here's another example of the complexity. This is the Lynxview fire that happened in the Blue Mountains in 2013. So just to put you in context, this is the town of Penrith, and the Nepean River, and this is the vast expanse of the Blue Mountains. So this fire occurred here, spread down here, burnt down 200 houses. So the first obvious thing about just seeing that map is, well, how come the fire started there and not somewhere else? Because if it started here, it would have had very low impact, or here, or any of those places. So why did it start where it did? And obviously the impact that it has is very, very geographically specific. The second complexity is, even once that fire has occurred, how do we know where it's going to have its impact and where it's not? So here's an example of some of the houses that were exposed by that fire. And that's the before fire image, and this is the after fire image. So one of the big questions is, well, how come these two houses burned down and this one didn't? Or not this one in there that did. No, so the actual trying to understand the reason why the impact plays out the way it did is really complicated. But we're having a go, and people elsewhere are having a go also. And so the first topic then of those, where, when, what is where. So this is risk planning. So for a long time, fire management agencies have tried to understand and inform people about where the highest risk is. And typically that's been through this concept of bushfire-prone land. And really, this is an example from an area within Sydney, the northern suburbs of Sydney. And essentially all it really is a map of vegetation and a 100-metre buffer around it. And that's as complicated as the risk plan gets. We're trying to move into a more sophisticated idea of where the risk is, because that particular patch of bushland and the houses around there, I can assure you, doesn't have the same risk as an equivalent one somewhere else, or as another patch of bush that's connected to a major forest. The risks vary greatly. So one way you can look at risk is simply by analysing the pattern of historical fires. So here's an example. It's simply a density map of where the ignitions have occurred. And so you can see Sydney in the middle there, and then you get these real, very obvious hotspots. These are the areas around Gosford, and this is Royal National Park. These hotspots tend to occur in places where you've got extensive bushland but right next to built-up areas. Then you can go one step further and to say, well, where in this landscape would you be at risk if a fire started in different places in this landscape? And that's the approach that a lot of the fire agencies are now going towards, trying to produce maps, that sort of nuanced maps of risk. And they typically use simulation methods to do this. And I'm going to talk a bit about those and also alternatives, because there's all manner of ways you can work out how fires are getting spread. So I myself have developed an empirical method that more or less does the same thing. So here's some examples of use of simulation models to map risk. This one on the left-hand side is this is what the Department of Environment, Land, Water and Planning, DELP, in Victoria do on a routine basis. The City of Melbourne, and then these are hotspots of places where if fires occurred, these would be at high risk of large numbers of houses being burnt down. Essentially what they do is they put a grid of ignitions every 2 kilometres. They start a simulated fire across here, and they do that they repeat that under many different weather conditions. They run this bushfire spread simulator, and then they just count up the areas that get impacted. And of course, the areas that get impacted are the places where the bush comes right up to the towns. So, for example, a couple of examples. This is Kinglake. So Kinglake, although they had a bushfire a while back, as you know, still at very high risk. And here's a really interesting one. This is the Dandenong Ranges that so far, since Ash Wednesday, they've escaped. But I don't think they're going to escape forever. They're going to have a big fire in there somewhere sometime soon. And then this is your local example that Jamie did for a recent paper. Same sort of approach, I think, where you just put hundreds of thousands of simulated fires across the landscape and look to see what happens. In this case, this is simply a map of the fire intensity, and it's highlighting the fact that, lo and behold, Hobart seems to be the most at-risk area in Tasmania. And then this is an example from one of the areas, suburbs in north of Sydney, that our rural fire service have been working on. And again, so in this example, this is where all the built-up area is. This is all forested, and they're saying the highest risk is essentially in these areas here where you've got quite a lot of forest and a few houses. So that's essentially places all around the world are now doing this sort of approach. Here's another way of doing this, essentially the same sort of thing, but in computationally much faster. Because the basic thing they're doing is saying, well, you've got a possibility of a fire starting here, and it's going to spread through a bunch of fuel to possibly impact or not onto a house or a map of houses. So you don't actually have to recreate fires each time to work that relationship out. And so here's a method that uses a statistical approach. So basically you see the purple areas there, historical fire maps. And what we simply did was to sample from the ignition point of that fire, to pick random places in the landscape and simply ask the question, did the fire get there or not? A binomial statistical model, and where the predictors are things like, well, how far away were they, what was the fuel, what was the weather on that day, that sort of thing. And the statistical model works quite well. Turns out to be about 98% accurate, predicting whether or not a fire will spread to a particular place in the landscape. And you can use that to produce a risk map. So here red is places that are more likely that if a fire were to ignite in the landscape near there, that it would reach an asset. It's not really saying whether or not that would burn down, but it would certainly go to reach. And so here, for example, this is the road going up the Blue Mountains in New South Wales. Because fires can reach them from both sides, and there's lots of fuel, that turns out to be one of the very high risk areas. Nothing too amazing about that, but the point is that the method, in a way similar to the simulation method, it's objective. In other words, you can compare the value there to the value there in an objective way. And here's another example where I've applied this technique in the same way. You sort of reverse engineer this equation to develop this, reverse engineer it, and you get a map here, which is quite similar to the one you just saw, the map that they produced using the simulation method. That's the one using this statistical method, and they're quite similar. They're not identical. One of the interesting things is that the simulation method found that a lot of fires starting out in this area, but they never crossed the river. This is the Nepean River crosses here. My method sort of doesn't do barriers very well, so its incidence is quite high. But the really strange thing is that in actual fact fires have crossed that river in the past and have impacted. So it's a sort of a way of saying no method is perfect with any of this stuff. Now, so those models essentially give you some sort of a probabilistic surface of whether or not fires are going to reach assets. You can actually add the consequence or the impact into that by essentially combining with maps of consequence. So that could be vulnerability. So, for example, people have been working on mapping out where frail people are, people who are not going to easily be able to get out of their houses, mapping where restricted escape routes are. This is a real problem in Europe, for example, where a lot of fires occur on these little tiny windy roads. And all of this can be done essentially in that statistical method. All you have to do is prepare a map like that, and then just by multiplication you can combine it into a likelihood and consequence map. And in the same way, you can look at models of house loss. So I'm going to do we've got some examples of house loss research. And so essentially, if you've got a statistical model of house loss given a fire, you can just multiply it by by the likelihood maps, and you've got the two combined. And now we're going to talk a little bit about smoke, because this is where I'm going with my research now, and so the where of smoke. So we have, in Sydney, we have had some episodes where the entire city has been smoked out, and big deal. The epidemiologists estimate that lots of people get killed in these events, or the number of quality of life, or number of years lost, I think is the best measure. So that's a wildfire in 2001. This is a prescribed fire in 2016 that essentially smoked out millions of people. So what some of the big questions are, is there a consequence to doing prescribed burning? Because we know that it has some sort of a benefit in terms of reducing the amount of wildfire, so reducing the area of wildfire or the intensity of wildfire, but is there an unintended consequence that you're exposing people to more smoke? That's a really complicated thing to work out, but that's essentially what my project over the next 4 years is trying to do. So we've had some baby steps. So a couple more examples. So this is another case of a prescribed fire that happened earlier this year, May the 10th. And you can see from a MODIS image that that's a prescribed fire, but its impact is not small. This is the size of the smoke plume. And that produced another event, something similar to that one. We got some actual measures. It doesn't matter exactly what it says here, but the point is that several of these air quality stations around Sydney, several of them are into the orange. This one is an exceeding, so that's gone over the national standard, and that one there has gone over the national standard. Melbourne gets this even worse than Sydney does. I'm not quite sure what the situation is in Hobart, but you do get some bad days. So one of the things that we've been doing, Stephanie, who's in the audience here, has been doing some work mapping smoke plumes. So that is essentially to say smoke plumes that you can see from the MODIS imagery. So that's about a 500 metre resolution image that comes across. There are 2 images a day, so if the day's not cloudy, you can map any smoke plumes. And she's mapped about 700 of these plumes and combined it with some data that's been produced before. So Grant Williamson did a whole bunch a few years ago, and I've done led some work where we did some more. And now, so this is the number of smoke plumes that have passed over any place in the landscape in the Sydney region. So that's the city of Sydney. This is the Blue Mountains. This is the Wollongong, the vast wilderness out there. So this is prescribed burns. This is wildfires. The numbers are a bit higher for wildfire, so red is a little bit more. But so what you can see is, so this is where the smoke from wildfires goes, and this is the Wollongong National Park. So most of it is essentially in the massive forested areas, and it also means that although it does spread, most of it doesn't spread that far. Now I'm just going to go back to that prescribed fire one. Not the same story at all. So these are the northern suburbs of Sydney, and that's one of the most exposed areas for prescribed burns, smoke. We're not sure whether that is smoke that's come to the ground. It could be staying up in the air, but that's what some of our researchers are going to do to work out whether that's actually had an impact. Because if that is coming down to the ground, that's potentially impacting people's health. And it's sort of saying, you know, what we're doing here is we're trading off that for that. And there's a consequence to doing that. Okay, so I've done where. So now we're on to when. One of the major challenges is to working out whether or not a fire is about to occur, or is it going to occur this season, is it going to occur this week, is it going to occur today? And so it is a sort of a temporally scaled type of thing, and we start with this seasonal outlook. So this is a seasonal outlook that the Bushfire CRC produces every year. Usually just says the whole of the country has got high likelihood of having a bad fire year this year. Extraordinarily blunt instrument. And someone's done some research. So Hamish at our centre has done a research and said that's actually more often wrong than it is right. So seasonal outlooks are extraordinarily difficult to do. This is more like on a weekly basis. So this is work that Ross and some of his colleagues have been working on, which is to produce maps of fuel moisture. So every week, the MODIS satellite images are collated. I think they're averaged and so mapped at that sort of scale. And you can see, if you saw a whole sequence of these images week after week, you would see how the landscape's drying out. And these correlate extraordinarily well with where the big fires have occurred in the last few years. So on a weekly basis, you're starting to get some sort of discrimination to be able to say in New South Wales, we would be able to say, the northern forests are likely at high risk this week or this month, and that zone of risk is sort of moving slowly down the state, and now it's affecting the Blue Mountains, something like that. So that starts to become far more useful. But we'll never really be able to predict exactly where a fire is going to occur, because this depends on this human agent, who's going to actually start the fire. Or a fair proportion of them are started by lightning, and it's very difficult to predict where a lightning strike is going to occur. Once a fire is started, there's a lot of effort in the fire management agencies to try and work out what the impact of that fire is likely to be, and essentially that revolves around fire behaviour modelling, and all the states, I believe all the states really have some sort of capacity to do this now. And so I'm just going to run you through this example. This one has sort of been matched to fit, so when they first ran this is the Kilmore fire in 2009. I think when they first ran it, it didn't predict that well, but nowadays they've tweaked it, so it reproduces essentially what happened in the Kilmore fire very well. It started over here, and this is the town of Kinglake and Kinglake West. The fires did do more or less this. It spread down past and then blew out, took out the town. And that sort of thing can loosely be predicted. So that's essentially all I wanted to say about forecasting, predicting, and get on to the other major topic of mitigation. So that's understanding what factors make it more or less likely that you're going to have an impact, and once you can do that, once you've done that, you can start to think about how you mitigate it. So this is a really, really complicated story because there are so many elements at play, but we tend to break it down into what you can do about ignition, because if you could stop them before they start, obviously that's ideal. Initial attack, suppression. So initial attack is what you do immediately the fire is reported in. Suppression on large fires is what you do once the fire has missed that initial containment. There's fuel management, prescribed burning, which is one of the major tools that the agencies use. There's what their term called defensible space, which is really about managing fuels around houses, what the house is made of, what people do in a fire. So I've called that defence. And then because I've got this interest in smoke, I'd say something about smoke impact. So the first one of these is ignition. So at the moment, ignition is extraordinarily difficult to do anything about it. The agencies at the moment introduce fire bans, total fire bans on days of high fire danger. That's about the most sophisticated tool they've got at their disposal. There is some evidence that it does work. You know, it's not going to stop all fires, but it does reduce the number of likely ignitions. So Matt Placzynski, for example, has got a paper that suggests that it works. Ultimately, if everyone was aware of how much risk there was if they started playing around with matches in a bad fire day, I think we could get better. But that's a whole social science thing that very hard to get into. Agencies have, they do have these programs, but how effective they actually are, I'm not sure. I was just going to say a bit about power line management, because power lines don't often cause bushfires, but when they do, they're really bad. So here's some data from Katie Collins' work. But essentially what she's shown is the grey bars are the proportion of all causes caused by this cause. So majority of fires that occur are deliberate. Only a very few of them, about 3%, are caused by power line failures. But the black lines is the ones, the same proportion, but of fires that actually cause houses to burn down. And that goes from being 3% to something like 12% of fires that cause house loss. And in fact, if you actually work out as a proportion of the number of houses that are burnt down, power lines become even more important. The issue is that power lines tend to fail under extremely bad weather, so when it's really hot and really windy. And so I believe that tackling power line ignitions is one of the biggest challenges, and one of the things that would be most effective if we could do it. I mean, you're not even going to do anything about lightning, which is this one, but you could do something about power lines. But the bottom line is the overall story with the ignitions, it's pretty hard to do much about them. Oh, there is the lightning, the power line caused the fire. So the second one was suppression. So initial attack. Initial attack is what you do when you first report a fire. So it's sending crews out, it's sending helicopters to douse the flames. There's been a fair bit of research on this topic, and it turns out that it is very effective. One of the things here is that the research is quite easy to do compared to what happens next if they can't get this fire under control. So it's quite easy to work out that it's effective. But if you're not effective, you get into this what we call suppression of large fires, or campaign suppression. And that's where you're starting to send lots and lots of fire resources, and they're doing all manner of different things. And it turns out to be very difficult to work out how effective they are. And partly because the record keeping doesn't actually tell you a great deal about what is being done. And the thing is, it's very difficult to be able to predict what would happen had those fire trucks not been at that spot there. One of the ways that people have done this in the past, recently, and we've been involved in the project, is using simulation to say, so we know where the fire perimeter actually was for that fire. What would it have been like had those fire suppression resources not been there. So you run a simulation to say, well, where could that fire have gone? And that is also fraught because simulators are not that accurate, but you can have a go at it. So, for example, so these are some of the things we did, but this is an example of one of the projects we did, where this is the actual fire, and we ran simulations with our suppression, as we understood from the records, what happened under that suppression, and we get another fire size, and then we run it again with no suppression at all, and we get this very large one. And so these are the results. So that for that particular fire, you add up the costs. So what was actually lost in economic terms, what the suppression cost in economic terms. So that's $8 million spent on that fire. The losses that we predict from our simulation model without suppression and with suppression. In this case, it was really, really different, and we get a ratio of 14. So that was essentially, this method is able to tell you that for every dollar they spent on suppression, they saved $14, which sounds great, but you have to bear in mind that the simulation methods are not brilliant. Here's another example of a fire where the opposite happened. They actually ended up, when you add up the losses and the costs and what they potentially saved, they actually spent more money than they needed to. And from what we can tell from our study, the main difference is suppression is very, very effective when you're in a grassland fire or a mixed situation where fires can break out and spread very quickly. And in the grass, they're quite easy to suppress. If you're in a forest, it's very hard to get a return. Now, very early days, and I'm not saying that is the actual result, but we're starting to get some information about suppression effectiveness. Prescribed burning is one of the areas that I've spent a lot of my time doing research on. Prescribed burning, obviously, the idea is that you remove fuel from an area so that if a wildfire comes along, it's less likely to have an impact. It's either going to stop or slow down or be of lower intensity. So there's been all manner of research on this. So looking at rates of fuel accumulation, how prescribed burning affects area of wildfires over the longer term, how prescribed fires affect fire severity and fire spread. And I'm going to run through a few examples, but I'm just going to mention that the problems are that fuel recovers very quickly. Typically 2 to 3 years after a prescribed fire, you can have another fire in an area. We've also found that prescribed fires don't seem to have a great deal of effect if the weather is extreme. So Black Saturday type conditions, even something relatively recently, but prescribed burns is not going to do much to stop a fire or reduce its intensity. And the bottom line is, so most of the prescribed burns that are put in end up not being of any practical use because they never encounter a wildfire. They just grow back to their pre-fire conditions before a fire occurs. So all this suggests that prescribed burning has a modest effect, and it needs to be quite carefully targeted. So I'm just going to give you some examples. So this is the fuel accumulation curves that are typically used for wet and dry sclerophyll forests in the New South Wales. And so you can see immediately after a fire, the fuel's gone down, but in the dry sclerophyll forest, it's gone up to a level of 8 tonnes per hectare, which is generally considered to be high hazard. That's after about 3 years. And in a wet sclerophyll forest, it's got there in about 1.5 years. And then here's another example from some study we did recently, which is saying that we suspect that one of the things that might be going on in some of these dry sclerophyll forests is that after you've had a fire, the shrub layer, so this is the relative, this is the shrub layer cover score taken from thousands of plots from the New New South Wales Botanical Survey database. The interesting thing was that time since fire relationship with mid-story cover suggested it actually increases for a few years after fire, then goes back down again. So that 10 to 15 years post-fire is at its maximum. And this is probably something to do with this. This is a post-fire regeneration of acacias after the Wombalong fire in the Warrumbungles. I think this is 2 years after a fire. The fuel loads in there are far higher than they ever were before the fire. And then, so I was going to say a little bit about what we found with relationship between prescribed fire and severity. And so here's an example from the Black Saturday fires in Victoria. As you presumably know, they're probably the most intense, or certainly the most impacting fires that we've had in Australian history or recorded history. What we found was there is a relationship between how recently an area was burnt and how likely it was that the area would have a crown fire. And if the weather at the time was moderate, there's a pretty good relationship. If the weather at the time was catastrophic, so FFDI above 100, you're going to get a crown fire no matter when you were last burned. And if the weather was really mild, you were not going to get a crown fire, and it didn't matter when you were burnt. Another is a more recent study we've done in probability of crown fire occurrence with time since fire. This is using 23 fires in New South Wales. We found this interesting result that, of course, just after a previous fire, there's very little chance of a crown fire, but it actually goes up to a peak at around 10 years, and then, I don't know, something strange might be happening after that. But the point is that it doesn't go up to a peak and stay there. It goes up to a peak and then comes back down again after 10 years. And then this is more recent work that one of my students has been doing. And this is sort of asking the question is, what's the likelihood of having a high severity, so crown fire in a plot, compared to what the severity of the previous fire was? And he found that you were more likely to get crown fire if the previous fire was crown fire. And that sort of relates, we think that relates to this previous thing about this shrub recovery. So the more higher the severity is, the more vigorous this shrub recovery is. Okay, so that's prescribed burning. The next one is defensible space, so what you can do around your house. So lots of fire agencies here and in the United States, for example, they have this concept of defensible space. And so what it is the zone around about 30 metres around your house, which is not only is you will be relatively protected if you keep the fuels low in that area. It's also called defensible spaces because it's safe to be in. So fire trucks and fire crews will attend to houses that have good defensible space, and if they don't have good defensible space, they probably will go past you. So it's important from the point of view of the fire crews, but it's also important if you want to defend the house yourself. So this is important things here, and these are things that have been statistically shown to be important. Trees overhanging the house, not a good idea. Vegetation within 2 metres of the house, not a good idea. And then there's evidence is not quite so clear, but it seems pretty obvious. Man-made fuels like having your things like tanks of fuel, bottles of fuel and stuff like that, or gas bottles very close to the house, stashes of firewood underneath the house, things like that, all very risky. So here's just one example. That's a house with good defensible space, and that's one with poor defensible space. House construction. So this gets quite complicated because, as you can imagine, there are so many different aspects of a house that can or cannot facilitate a fire getting into it. In Australia, we have the Australian standard AS3959, construction in bushfire environments. The idea with this is that a house is designed to withstand heat, direct radiant heat from fire nearby. If you're 40 metres away from bush, you don't really need to bother. But anything less, you start to have to increase the standard of construction to withstand that heat. One of the problems with this standard is that most houses don't burn down because of radiant heat. They burn down because of embers, and this standard doesn't address embers very well. It does to some extent, but for example, you are not allowed to have gaps more than 3 millimetres wide in between the tiles or in between the roof and the fascia boards. But 3 millimetres is actually too big. The embers can get through that. The other thing it doesn't do, if we're going to go back to this example from the Linksview fire, the other thing it doesn't do is the way that this is applied, it assumes that the bush or the mapped vegetation is the source of risk. It takes no notice of the risk posed by houses nearby. So this is actually that from this fire. This is a map, line scan map taken when the fire front passed through, and that's the fire front there. And these are all the houses that are burning. So it's almost certain in this fire that the main source of risk or heat, say to that house there, wasn't the bush, it was the house next door. A lot of houses are burning down from house-to-house transmission, and our official standards don't take that into account. And the other thing I was going to say about there is reasonable evidence that the standard houses built to a higher standard, according to that standard, do survive better in fires. But an even better predictor of whether the houses will be lost, this is data from this same fire again, is what year the house was built. So this is the proportion of houses damaged against the year of building, and so the most recent ones really haven't suffered badly at all. But as you go back, especially the really old houses, there's only N1 I think for that one. But yeah, that's age of construction.
Haven't been built yet, obviously.
That is a bit odd. That is a group, so there's some 2013 ones or 12 ones in there or something like that. Anyway, the point is that's a better prediction than the actual standard of construction. And what we think it is houses can be built quite well, but over time their standard deteriorates, and it's most likely something to do with the garden vegetation just gradually building up. Next one, getting near the end here. Defence. So it's been known for a fair while that defending houses is quite a good way of stopping them from being burned. It sort of makes sense. And that defence could be done by firefighters or it could be done by householders. Apparently, the evidence we've got suggests that it doesn't make a heck of a lot of difference who's doing the defending. But of course it is risky and should be only attempted by people who are physically and mentally prepared. And I think fair to say you need a place of last refuge, because if you're in Black Saturday type conditions, some of those houses, even when they were defended, were still burning down. So you need some place of last escape. So we do have some data on this, and so first of all, for that Linksview fire again, for those houses that were defended, only about 15% of them were damaged, whereas some were more like 40% for the ones that weren't damaged. And when all the different factors that we measured for this fire, so for that particular fire, we perhaps for the first time tried to assemble all the different factors that could have been responsible for house loss. So we were talking about the house construction, whether they were defended, what the weather was like, where the vegetation was, all of these different factors. When we tried to combine them all into a single statistical model, a random forest model, the single variable that came out the most important was whether or not it was defended. The next one was construction year, And the third one was distance to forest. So this is the first one that's really to do with fuel. And then construction level aspect, and then where it was, which way it was facing with respect to the fire was important. But the thing is to notice is these ones down here, defence is the main way to protect a house. You know, this is from a policy point of view, this is really difficult because defence is putting people in potential harm, but there's no doubt that it works. And then I wanted to say something a little bit about how to mitigate smoke impacts. And essentially, not that we have an answer here, this is more like questions. But the question is, as I mentioned before, that we need to trade off you're saving a smoke impact from wildfire, and you're also saving a potential impact on houses from wildfire by putting in prescribed burning. But from the research that we've done on prescribed burning, it suggests that the best place to put prescribed burns is right near the assets. And as that map I showed you indicates, that is where prescribed burns generally are put in, and it does mean that the smoke is going to affect people because that's where it's being generated. So the question is, well, the questions are: does prescribed burning reduce the overall smoke or not? Does it shift where the impacts are felt? And can prescribed burning be managed to minimise smoke impact? So some of the things we do know and we're beginning to understand better is that the impact that you have in terms of smoke from a prescribed burn, it depends on such things as what time of day you light the fire. So if you light it maybe as late as 2 hours later in the day, the smoke could be a lot more buoyant. So then if you light it at 9 o'clock, it's going to hang around quite low. Compared to 11 o'clock, it might go a lot higher, it might blow away easier. And of course, you can also, in the United States, for example, prescribed burns, or at least in Florida, all prescribed burns, and they have 90,000 prescribed burns a year in Florida. Every single one has to do a smoke prediction to work out, predict where they think that smoke's going to go, and they're only allowed to do it if the wind is taking the smoke out over the ocean. So similar sorts of approaches could be done here. Oh yeah, I was going to show you this. So this is actually an example. I have started looking at the air quality data from New South Wales, and so this is an example of the exceedances. So the exceedances days when this is at Liverpool in the sort of inner outskirts of Sydney. Exceedance is a day when the average 24-hour reading is above 25 of particulates, PM 2.5 particulates. So that's a bad smoke day, and we're comparing that to all days. And so essentially what we're saying, and this on the x-axis is the strength of the temperature inversion. So that's saying an inversion is where the air gets warmer as you go up from the surface. So this 10 degrees is saying that it gets 10 degrees warmer before it starts getting cooler again. And what we say is on average you don't really have any sort of an inversion. But on days when you have an exceedance, you generally do. It's a very strong relationship. Most exceedances occur on inversion days. And then here's one other interesting feature. So this is a different source of data, but it's also from Liverpool. And this is the cloud of points is the actual mass of particulates taken on a daily basis. And there's a GAN model fitted through that, so you wouldn't see it otherwise, but there is a very strong seasonal relationship in the amount of particulates in the air. And the peak is in July. And July is not a bushfire time of year. It's not even really a prescribed fire burning time of year. So it's pretty strong evidence that this peak is caused by wood-fired smoke, the same problem as you have in Tasmania. So our challenge in our project is to say, well, okay, if the main ones are caused by something else, and we're trying to find the impacts from prescribed fire, we're trying to find how possibly we need to try look in this area these are almost certainly going to be bushfires. Maybe for prescribed fires, they might be these ones. So it's like on the shoulder. This is the time of year when you get prescribed fires, and for some reason these are particularly high values from what it ought to be that time of year. So it's just an illustration of how difficult our task is going to be to try and work out the impact of any particular fire on air quality. And so just a summary. So I showed you some examples of bushfire planning, which is, I think it's progressing along quite nicely. We've got some good tools now that can enable you to map likelihood. Forecasting, I think, is still really, really difficult. All three scales. Mitigation, we're starting to get a handle on the most important strategies, and I'd sort of highlight such things as that role of defence. Defence is really effective, and also the problem with power line ignitions. It's something that could be addressed if we had the will and the money to do so. And I think with that, I'll leave it there. Thank you.
Thanks, Owen. Well, I think that was an absolutely terrific way to start the seminar series from the Fire Centre. That, if you don't know, is pyrogeography. It's complicated, and it's the intersection of atmosphere, land, biodiversity, humans, the full catastrophe, to excuse the pun. And I think that's what I really liked about Owen's talk is how systematic the thinking is. It's really laying out the sort of the breadth, and you can see from that all of the dimensions, matters arising of planning, law, perception, psychology, risk, personal risk, societal risk, dollars. That's it. That's the full package. And I think one of the problems that we have in universities is that thinking about these problems totally atomised, that the people who are produced by the universities really have to be reskilled when they enter into industry. And just being able to keep up with this, if you're in the industry, there's a lot happening. And that's why I think it's fantastic that the investment the New South Wales government's made to really bridge that using the capacities of the university sector, but also making certain that it's very directed, focused on very outcome driven. So thank you. And I just thought we've got a little bit of time. I think we're going to be booted out here exactly on the hour. But I'd just say Owen's here, Ross is here. We'll go outside, have a chat if you want to have a chat, because it's part of the thing of the Fire Centre is networking, and what I'm wanting to do is a lot more overlap with the work we're doing in New South Wales at Tassie, and certainly internationally. And you can see Owen's got that flavour, but you may have some questions, and then we'll just have a few questions, and they'll be outside. We can have a chat, maybe go and grab a bite to eat or something. So any questions? Chris?
And you mentioned a couple of times that the fire models are still pretty ordinary. What has to be done to make them better? What's the problem with them? Can they be improved?
How long have you got? One of the big problems is that they all use an underlying fire behaviour model or set of fire behaviour models that were developed under a fairly restricted set of conditions. So MacArthur is the most commonly used one. That was developed essentially on forest plots and experimentally, and they weren't going to set light to those on extreme fire days. So we don't have any. The model doesn't extend to extreme fire days, and there has been some work to show that in actual fact, under extreme fire days, that model underpredicts by a factor of 3, quite likely. By the same token, it probably is not working very well on the other end either. They're extremely mild fires. Another problem they have is it's very hard to get the weather accurately, because weather is recorded at stations that could be 10, 50 kilometres away, and there's all these means of sort of interpolating between stations, but none of them, I don't think, work that well. Another problem is that the fuel maps are not that good. They're very coarse. I mean, that's actually a problem for whatever method you would use right now. You can't get a good fuel model because, you know, essentially what you're saying is that's a particular type of dry sclerophyll forest, so the fire is going to behave the same way all through that entire patch. But we know that, you know, at the top of the ridge it's different to the side, and it depends on the aspect and all those sorts of. None of that's factored into the model.
Leon.
Yeah. People are fairly rubbish at understanding probability, and I don't think that's changed since Savage working in the 50s and so forth. So how does this play out in the sort of management space when you present people with probability estimates from scenarios, for example? You feel that managers are getting better at sort of coping with probability statements, or?
I have a feeling the managers, certainly the ones higher up, do. I mean, in a way, they're. So when I was talking about that sort of the planning part of it, they're pushing the planning quite strongly because they see the value of instead of being pretty woolly, what they do now. That's quite likely. That's not likely. They understand that if you could put numbers on that, that'd be useful. How it actually plays out on the ground with people who are firefighting or householders, certainly that's another story altogether. But the senior people.
The conclusion is simply drawing out of the controlled burning mixtures that doesn't make a heck of a lot of difference, and so therefore trying to communicate fairly modest. That's a really good point. Actually, this is the idea of residual risk. It will reduce your risk, but it doesn't eliminate it. I think that is quite difficult for people to understand, and something probably we have to keep hammering. I know in Victoria, and I showed you one example of what the government does in Victoria, and they put a strong emphasis on residual risk, what's still there.
Sue.
I was really interested, you said that prescribed fires don't do much when a subsequent fire's under catastrophic conditions. I've always sort of wondered whether, say, wet forests, wildfires, if we didn't control the ones that come under mild to moderate conditions, would that reduce the probability of a very large-scale catastrophic fire? Can you comment on that, please?
Well, I guess in essence what you're saying is that turns that into a sort of like a big prescribed fire, right?
Yeah.
It's got some value, but in the same way as prescribed fires are not really helping under catastrophic weather, nor would that in most likelihood.
Yes.
On this basis of your statistics on defending property being really effective, it might be that it might be an artefact to the statistics that those houses that are defended because they're defensible. So people feel safe to stay there and defend it. Is there any way of checking whether that's an artefact in the statistics?
I think you probably could by doing some fairly very detailed analysis comparing the factors, but the method that was applied there was a random forest model, which ought to account for that. So in other words, in the model, everything is allowed to interact with everything else. So if it's got an effect, it's an independent effect. So there were, for example, there were defensible space, like vegetation measures in that model too.
Well, one thing you haven't mentioned, and that in the mitigation, is the green fire break, sustained thinning on the perimeter of settlements.
Yeah, well, I don't know that there's been a lot of actual data collected that can test that, but it's certainly a good idea. That's the idea that you put in essentially a green barrier, like a golf course.
Yeah.
Or something more natural, but still green.
However, your example from Linksview shows that distance to the forest edge has an effect on property.
Yeah.
So that's a sorry, but what
Yeah. But it's a conversation that I would expect once the trade-off is fully understood with the smoke.
Another interesting thing from that same fire, I mean, it was a very complicated analysis because essentially after a fire goes through, they collect something like